let me just recap what we saw in the previous hour, which is we were looking at Navier-Stokes equation for incompressible fluid with some external forcing, which is confined to the large scales. It is not a body force like gravity or Coriolis forces and things like that. It is some kind of a stirring mechanism which feeds in energy at large length scales. So we looked at, so we started from this equation, and it's under the incompressibility constraint. Incompressibility constraint, which means the divergence of Vi equal to 0, and links the pressure to the velocity field as minus del I Vj del J Vi. And therefore, it's not really independent thing. It is just another addition to this term over here, which shows up in Fourier. So this is real space. In Fourier space, what it looks like is del T Vi at this mode over here plus nu k square Vi k. That's that term summation integral d3p over 2 pi cubed m I j l function of k v j p v l k minus p plus I k. So that's in momentum space. So that's the other thing which we wrote down. Mi j k is proportional to I times k and then some projection operators. And then, so all right, there we are looking at this at high Reynolds number. So Reynolds number, which is VL over nu, is much greater than 1 when the nonlinear terms dominate in the equations of motion, and the solutions are quote-unquote random functions of space and time, and therefore it's easier to describe things in terms of a probability distribution, and the probability distribution is for in terms of the argument is delta V of R, which is essentially Vx plus R minus Vx averaged over, so if I summed over I, so it's delta V of R, which is the function of, which is defined in this manner over here. And one talks about the probability distribution, which is, that's what one in principle would like to know. What we, and it is supposed to be, this probability distribution is supposed to be universal in some range which we call the inertial range. And this inertial range is defined as some L0 much greater than R greater than L0. This is where the inertial range is, and we calculated L0 over L0 to be proportional to Reynolds number to the power 3 by 4, so that for large Reynolds number, the scales are well separated and the inertial range exists. So in this inertial range, you have universal properties, and what we found was that the overall energy balance, E is the kinetic energy per unit mass, which is V square R D3 R, and this balance is given by minus 2 nu integral grad V square D3R plus epsilon, which is the rate at which I'm injecting energy to the system. That's this. So you have a steady state where epsilon, so steady state where epsilon is equal to nu integral gradient V square D3R, that's 1 over B. So that's what tells us that the interesting, the nu going to, if nu goes to 0 becomes arbitrarily small, it still is epsilon. So this grad V square has to become arbitrarily big, and that's where which means that this difference that we talked about over here for small grad V, for small r, small r is now well defined. Small means that it's much smaller than this L0 over here, but not so small that it runs into this L0 on the other side. So that this r in the inertial range, so-called inertial range, this delta V of r has interesting behavior, has singular behavior at small r. So that's what that singular behavior would ensure, that there is some divergence. There is a divergence in this integral, which would, counter the nu going to 0 limit. So this integral becomes arbitrarily big as nu becomes arbitrarily small, and you still have a finite epsilon. So that's the that was that. Then we had this question of the final answer, final picture. There is no answer really. The final picture is that here is this L0, or in terms of wave number, it is the large wave number, which is K0. There is L0 over here, K0. This is the input range. This is the dissipation range, and in between over here, there is the inertial range, where things are universal and determined only by the epsilon and the local scale, with be it r or be it k. So the local scale and the epsilon, because it's a picture which is tight. If I look at the transfer of energy, which we did by looking at E equal to Vk V minus k d3 k, and we looked at the E of what is E of k at a local scale, which is Vk V minus k, the an average value of that over realization, the probability underlying probability distribution, and we looked at E dot and found that it is some integral over d3p with this triad of velocities, one at p, one at minus k, the other at k minus p. So 3 velocities over here, some prefactors with m's over here, and this is the local E dot k which we have, and it is this triad which is of interest P, K, P minus K, K minus P. So you are transferring momentum from one scale to other scales, and the assumption is, so the nonlinear terms are transferring this energy, and the picture is that this transfer rate is epsilon. So this transfer rate is independent of scale. So the transfer rate is scale independent. So I have a very tight transfer picture that it goes in this inertial range from scale to scale in independent of the scale itself, and that completes the picture that everything over here, that there is this, if I look at any quantity over here, then that quantity in this, there is only epsilon, and there is the local scale, which is in r in coordinate space or k in Fourier space. So things are going to be determined by this constant scale independent energy flux going through from large scales to small scales and things over here. So if I look at the energy, for instance, the so E total energy, which the spectrum, defining the spectrum by E of k dk. So if I look at E of k will have to be determined, epsilon would have to be there, because if I put in, pump in a larger number of amount of energy, the energy spectrum would contain a larger number of energy. It is dependent on k, and so it would have a larger, it would depend in k in some interesting fashion. And so there is going to be, but nothing else, nothing about the system, not how you, what kind of manipulations you were doing over here, what kind of dissipations that I have over here, they have become irrelevant. And this is why this is the, for the theorists, very nice range, that this inertial range where things are universal. And in this, then, dimensional analysis would do the job, that E of k that I have over here, E of k will be determined only by k and epsilon. And if so, I can do a dimensional analysis. E of k is a transfer. So E over here is the energy per unit mass, which is L square over T squared. K is 1 over L. So Ek is L cubed over T squared. And K is 1 over L. And epsilon is the rate at which energy is being fed into the system, energy per unit mass. So it is L squared T squared times 1 over T. So that's the dimension of energy. So if E of k is k to the power alpha, epsilon to the power beta, then you have L cubed over T squared is equal to 1 over L to the power alpha, L square over 2 cubed, so L to the power 2 beta, 3 to the power divided by T to the power 3 beta. And if I compare the two sides, I immediately find that beta is equal to 2 by 3. And if I then have 3 is equal to 2 beta minus alpha, and 2 beta is equal to 4 by 3 minus alpha. So alpha is equal to minus 5. So this is equal to epsilon, some constant. There is a numerical factor over here which I can't get. So there is some numerical constant C, which is dimension, just a number like 1.5, 2.2, whatever. So it is C times epsilon to the power 2/3, and it is K. So that's the Kolmogorov 5/3 law. That's where that it's comes from a dimensional argument, and but the dimensional argument comes from a picture. So there is a picture which is important, that there is some, there is this energy which is getting dissipated at small scales. Unusual things are happening at there is dissipation at small scales. Steady state means that the dissipation has to be equal to the forcing of energy rate, and all right, that makes life, that's a strong constraint of on the system, and then you make the, you further sort of put this constraint on this picture that the input rate over here, the dissipation rate over here is also the same as the transfer rate from one scale to another. So it has to be the same epsilon going through, and therefore there is a dimensional analysis possible that E of K over here is determined entirely by epsilon and K. And similarly, if I talk about this delta V R raised to the power n, the moment over here is again going to be determined by epsilon and R. And so you write this as some constant Cn, which from n to n it will change, is once again epsilon to some beta and R to some alpha, and this has the dimension of velocity, so that's L over T, so it is L to the power n, T to the power n on this side, and you have epsilon, the rate L, 2 beta, 3 beta, and this is L to the power alpha over here. So these, this is what has to match, and that makes your 3 beta equal to n. So beta equal to n by 3, and n is equal to 2 beta, which is 2n by 3 plus alpha. So alpha is equal to n by 3, and so consequently this is equal to C over n epsilon to the power n by 3. So this, all this in the inertial range. In the inertial range, you have these moments come out as an epsilon to the power n by 3 r to the power n by 3, and for n equal to 3, for n equal to 3 actual calculations, I mean, that is, you start with Navier-Stokes equation, calculate the 3-point function, actual calculation gives you C3 equal to minus 4 by 5. So that's, which is, the answer is consistent, I mean the actual calculation consistent with the naive dimensional argument, and also gives the coefficient over here. So this is the this is what you have at the end of the day, that you have sort of put your faith in some picture which is drawn with some very broad strokes, that there is a total energy conservation. So total energy conservation over here, you have put a steady state and a total energy conservation, and that has given you a constraint. That constraint, mind you, has another very interesting feature. The interesting feature is the fact that look at this relation over here. Because of this term, Navier-Stokes equation is not invariant under time reversal. So if I did a time reversal, and so which would set t going to minus t, and v therefore going to minus v, this term does not change sign. This term, which has two v's, does not change sign. This is just this term. But this term over here changes sign. So there is, under time reversal, Navier-Stokes equation does not have that's not a symmetry of the system. Time reversal invariance is not there, which is quite all right because the viscosity is a dissipative term. So in the presence of dissipation, there is an arrow of time, and therefore time reversal invariance is not there. But then I expect that if nu goes to 0, the symmetry should be restored. So time reversal is broken because of nu. Nu going to 0 should lead to a restoration of that symmetry, but this relationship tells you that even with a finite epsilon, even if nu goes to 0, this term has to remain finite, so that dissipation is still going to be there, and therefore in the limit, this time reversal which was broken in the presence of viscosity is not restored as nu goes to 0 in this situation, and therefore you would find the word which is often, this is referred to as dissipation anomaly. So it's an anomaly in the sense that you are taking nu going to 0 and you expect the symmetry to be restored, but you still, in the limit of nu going to 0, you still have a finite dissipation and the time reversal cannot be restored. So that is why this is a dissipation anomaly, and that's something which is what, I mean, it's interesting. If you look at there are two kinds of proofs of this relation, this n equal to 3 over here. One which, given in Landau-Lifshitz, depends on calculating correlation functions starting with Navier-Stokes equation and working things out and using the symmetry of correlation functions and so on and so forth, getting this result out. There is a different kind of calculation which you would find typically in fresh texts on turbulence and the lecture notes of F. David called Turbulence for and by Amateurs. This is this text, Turbulence, the Legacy of Kolmogorov, and this is an article which you will find called Turbulence for and by amateurs. So that's interesting. This is the different kind of derivation which sort of exploits the anomaly to get this minus 4/5 R. So worth reading. So there are two different, all right, I mean, that's a derivation which is interesting, and since it's the only exact derivation that can be done in this whole business, it's worth, extremely worthwhile. That essentially tells you everything about Kolmogorov, what you expect, what kind of results you expect from Kolmogorov theory, that there is this question of cascade, and there is a question of something happening, things being universal things happening in between two extreme ranges, and over there dimensional analysis can go to work. Yeah. Yeah, right, sure. Right, I mean the whole, that anomaly is that even in the limit of nu going to 0, which is Reynolds number, you still have a finite dissipation. Yeah. So it is, I mean, the anomaly refers to, I mean, the Reynolds number infinity. Yeah, go ahead. I mean, things don't need to be integrated over for dependence to disappear. I mean, if I have a k coming from here and the p integration giving me a 1 over k, things are gone. K is gone. So that's the. So this is it. So let's, I mean, see how far one can push this. Yeah, go ahead. Yeah. Yeah. How it? Oh, I mean, the point is that the fact that that there is dissipation in the is straightforward, right? I mean, there is viscosity, so there is dissipation. Nothing there, nothing else. So, but now, all right, comes here. It is not a problem. Fine, there is no. Now you are imposing a steady state. So it is imposing the steady state which is doing the job. You are imposing the steady state and then taking the limit of nu going to 0. That's the. So this two operations here, I mean, that you assume that the steady state is always going to exist, and that is what. Very good. All right, so all of you comfortable with this? Because now I'm going to take up another and ask you what's going to happen, right? So, what have we learned? That I look for conserved quantities, and once I have a conserved quantity in an inviscid unforced limit, I have the beginnings of a complication, of a cascade and what have you, cascading laws. So what else? I mean, I'm going to search for conserved quantities. I've looked at velocity square, and after velocity, the next thing which is where, I mean, Navier-Stokes equation is generally written in terms of velocity, but a very popular way of writing it is to take I got rid of the pressure by this prescription over here. I can get rid of the pressure by taking a curl. So I can write del T of curl of V plus curl of V dot grad V is equal to, here, so it is del square omega plus curl of F if there is a, right? Now curl of, so curl of V is what is called a vorticity. And so this is the alternative description of Navier-Stokes equation can be in terms of the vorticity variable when it is del omega del T, and then exercise, so assignment number 1 gives you some feel for vector algebra, that this curl of this chap over here is, this would be V dot omega minus omega dot grad on V. This is equal to the new. So this is what I mean. You can, that this reduces, taking the curl that this term is going to be, that as an exercise you can work out. This is the answer. So question number 1: do you expect omega square to be? So imagine these two are not there, and I'm looking at del T omega square d3r plus integral V omega dot with V dot grad acting on omega d3r minus integral omega dot grad V d3r. This is equal to 0. The right hand side, the forcing and the dissipation and the forcing are not there. So it's del T omega square d3r plus this minus this is equal to 0. So now what about this term over here? Do you expect this to be 0 or non-zero? Will you be able to show that it is 0? Let me write it out for you. It is omega L Vj del J omega L. Right? So omega dot this d3r. Correct? Yeah. So question is this integral going to be 0 or not going to be 0? Take vote. I see. All right. Okay. Well, in that case, let's leave it for the next another assignment. Show that this integral goes to 0. So this chap over here is going to go to 0. So this integral is going to be 0. But now comes the other chap. That's this one over here. This one over here, and this is not equal to 0. So this is not equal to 0. In fact, that is actually the basis of this the turbulence mechanism of energy transfer, at least, I mean, there is a good school of thought which thinks that this is what is called the vortex stretching term. If I have a certain amount of vorticity in the system, then, I mean, this is the one which is going to sort of pump in vorticity to the, and the result is a vortex stretching. If I have a vortex tube which looks like this, in the course of, I mean, this stretching, it sort of looks like, starts looking like this, and there is, I mean, this sort of tells you that there is a transfer of energy from scales which look like this to scales which look like this, and the vorticity is driving force in generating turbulence. Turbulence, I mean, if you look at these pictures which books show, there are a lot of vortex type structures all over the place. So it's not a bad thing to talk about, that vortex stretching as the so physical mechanism. I mean, this term is very often used, pinpointed. One pinpoints that as the mechanism of for generating the vortex stretching term, which is the mechanism for generating turbulence and transferring energy from large scales to small scales. All right, so, but that's, right now I don't want to, I want to focus on what I have already talked about. Let's talk about d equal to 3. This is not working out for me. So d equal to 2. D equal to 2, omega dot, that means omega, this, what I have is, there is only no z. It's everything is in the xy plane, and we are talking about things which depend on x and y, and omega, curl of omega, which is curl of v, omega is curl of v, it's d equal to 2. What's the direction of omega? Perpendicular, right? In the z direction. So omega is in the z direction. So this has to be, this is omega del z of v vector, but it's 2 dimensions and things depend only on x and y. So this is equal to 0. Right? So in 2 dimensions, this term doesn't exist. And in d equal to 2, it is del omega del t plus v dot grad omega, v dot grad on omega. Omega is a scalar, so I mean, it's only in the z direction, which is equal to nu del square omega plus some, let's say, some g which is forcing vorticity into the system. So this is what it is in d equal to 2. And now integral omega square d to r is conserved. If nu equal to g equal to 0. So no so omega, integral omega square d to r is conserved in the absence of forcing and dissipation. Do you agree? Yeah? All of you comfortable with this? Because this is the, it's only this term which I have to get rid of, right? It is, I have to show that omega v dot grad omega d to r, that is equal to 0. So it is omega vi del I omega, and it is, so this is half vi del I omega squared, which is half del I omega squared vi. So it is a perfect derivative, and therefore it's a surface. So it's a divergence, and therefore So that's 0. So that part, this is 0, and therefore omega square integrated over d2r. That's conserved in the inviscid and unforced limit. Is energy conserved or not? Yes, right? And because when we talked about the energy conservation, this was a dimensionless, dimension-independent statement. I mean, when the way we work this out, it is not that things would be off in 2 dimensions and only work valid in 3. So v squared d2r, conserved if nu equal to j equal to 0, nu equal to, so no forcing, no external forcing, it's nu equal to f equal to 0, in this case f is so energy is conserved, vorticity squared, omega, this quantity omega square, this is d2r, this is s, the total, what's called entropy. So entropy, the omega square bit, and so that's a conserved quantity. Now I have the energy, which is also a conserved quantity. Now what do you think is going to happen? In d equal to 3, we were going along fine. There was only, this omega square is not conserved, only v square remains as a conserved quantity. So there is this Kolmogorov flow from one end to the other end. And, but here I'm faced with 2 chaps which are conserved in the inviscid unforced limit. There is this conservation, the entropy, and this both are order. So there is not obvious what the answer is. So there is a sort of low-level trick to low level, but not very bad. So it depends very clearly, very strongly actually, on this triad picture and that we had, where, I mean, you essentially added up you have a triad where the momenta sort of add up and give you a picture of the transfer. So I'm going to take a absolutely simplified model. I'm going to assume that there is only one triad of wave numbers. That there is only one triad of wave numbers, and I'll take them to be K1, K2, K3. And with this K1, K2, K3, I'm going to take this chap to be, let's say, K, and this to be 2K, and this to be 3K. The two of them. So let's, one triad, and the triads are, I mean, so K, 2K, and they add up to 3K, so that's the other chap. And now, since omega is curl of V, if I look at this at the in Fourier space, so it is omega as K vector, this is going to be like K in, if I were to look at this in momentum space, then omega K would be K cross V of K, And so this is a cross product, which means that there is a sine theta involved. So if I looked at omega square k, then this is going to be less than equal to k square v square k. So this is my entropy at wave number k less than equal to k square E of. So I'm in the business of making life trivial. So the point is, if along with this, I will make a assumption that of that less than equal to the, I'm going to work with the equal to. So I'm in the business of making things as easy as possible for me. So that's the next step of making it easy. So all right, now I look at the system at time t. So I look at this triad at time t, and then at time t plus delta t. I assume that there is a energy as you go from here to here. In mode 1, the energy has changed by delta E1. In mode 2, it has changed by delta E2. And in mode 3, by delta E3. The entropy has changed by delta S1. This has changed by delta S2. And this has changed by delta S3. Then I need to, therefore, these are the changes in going from time t plus. So delta E1 plus delta E2 plus delta E3 is equal to, equals 0. Energy is conserved. So the total energy sum over the modes is going to be 0. Entropy is also conserved. So delta S1 plus delta S2 plus delta S3 is equal to 0. Now, the wave number, the one is k. So delta S1 is k square. So this is k square delta. This means this goes to k square times delta E1. The next one goes to 4k square times delta E2. And the next one goes to 9k square times delta E3. So this is equal to 0. So delta E1 plus delta E2 plus delta E3 is equal to 0. Delta E1 plus 4 delta E2 plus 9 delta E3 is equal to 0. So therefore, I want to look, I will solve for delta E1 and delta E3 in terms of delta E2. I'm assuming that delta E2 I have given you, and I'm going to find the others. So if I do, then delta E3 is equal to minus 3 by 8 delta E2, and delta E1 is then minus 5 by 8 delta E2. Right? Then delta S3 is equal to delta S3 is K3 squared times delta is K3 squared delta E3, so that's 9. So 9 times delta E3 which is, and yeah, so now delta S3 is okay, is minus that's 333 by 9, so delta S3, that's minus, delta S3 is 9 times delta E3, which is minus 27 by 32 delta S2. Have I got it right? Delta S3 is minus 27 over 32 into delta S2, and delta S1 is then minus 5 by 32 into delta S2. Correct? Got it? Good. So, what I'm going to do, I'm going to assume that this was the middle of the range. It was K, 2K, and 3K. And I'm going to remove, so from 2K, which is in the middle of the range, I'm going to remove some energy, remove the amount delta E2. So remove delta E2, which means that delta E2 is less than 0. So I have lowered the energy in the mode 2K. The result is, which also means that the delta S2 is less than 0. So delta E3 is equal to 3 by 8 magnitude of this. Delta E1 is 5 by 8 magnitude of delta E2, and delta S3 is equal to 27 by 32 delta S2. Delta S1 is equal to 5 by 32 delta S2. So delta, so that's, now what does it mean? It means that in the forward, so what is the forward direction? This is going from what we have been talking about so far. From 2K to 3K is in the direction of increasing wave numbers, the kind of picture that Kolmogorov had. So whereas 2K to K is the reverse. So it is going from large wave numbers to small wave numbers. So from one length scale to larger length scales on this side, from one length scale to smaller length scales on this side. So if I look at the energy transfer, delta E1 is greater than delta E3. So more energy has been transferred in the backward direction than in the forward direction. So there is energy, net energy cascading towards the left that is going from one wave vector to a smaller wave vector. But so far as entropy is concerned, the delta S3 is greater than delta S1. So to the higher momentum side, it is the entropy which is transferring. So you have two conserved quantities and you have two fluxes. But entropy is the one which flows in the forward direction, and it is energy which flows in the backward direction. So here is, I mean, just heuristic arguments giving you a picture which tells you that the energy in 2 dimensions, the energy would be flowing backward. There would be from small length scales to larger length scales, and entropy flows in the normal manner from large length scales to small length scales. So both are conserved quantities, both have fluxes, but one in one forward direction, the other in the backward direction. If you now calculate the energy spectrum, dimensional argument, energy spectrum for energy, so energy flux back, that's backwards, and your E of k is the same argument, proportional to k to the power minus 5 by 3. It is determined by the energy input per, so there is this epsilon, which is the rate at which energy is being put into the system, and that's the same call. But then it's the entropy flux which goes forward, and now the energy spectrum E of k will be determined by epsilon s, which is the entropy flux. So entropy flux epsilon s, the rate of change of entropy per unit time, and you are supposed to do this and find out so that's assignment that find alpha and beta. So do the dimensional analysis and find what alpha and beta are. So there is, I mean, it is, I mean, whatever comes out is what is numerically seen, and also what calculations on based on Navier-Stokes equation do point out with a certain amount of rigor that the conclusions that you reach about this problem from conservation laws and just using the triad that we have set up over here, the triad for energy transfer, restricting myself to just one triad and getting an answer is not bad. I'll leave this part with a somewhat more difficult assignment for you. There is, in 3D, there is yet another conserved quantity in the absence of dissipative and forcing terms. There is omega dot v. This quantity is called a helicity, and h equal to omega dot v d3r is a conserved quantity. So that's, I mean, number one, I mean, you have to use Navier-Stokes equation and show that this is true, which will give you good practice. Second, all right, so if H is conserved, there has to be a flux. So energy is also conserved, and there should be, so energy flux we have already seen. So, and with the helicity also there should be a flux. And so number two would be use the same triad that I had over there. Use the triad. Now what about helicity? You see that this is omega is like k times v. So this is like h is less than equal to k times ek. There it was k square, here it is k, just one factor. So once again, use the triad and assume H equal to K times Ek, find, then, repeat the argument and see what you conclude, whether the energy you already know has a flux in the forward direction. Now with this, are things going to change? Is there going to be, because of the helicity flux, is the energy flux going to change in some manner? Or is it going to be that it's still going to remain a forward energy flux, and this helicity would have to flow? In which direction does the helicity flow? So find the flow direction. So if you, once you have done it up to that point, the final answer will discuss for the final answer will take just a few minutes to talk about. We can do that on Thursday. But as an exercise, these are, we have talked about conservation laws, we have talked about Kolmogorov argument, and so on and so forth. It's important to see that, having talked about it, is it simply one-off for the energy variable that we have talked about, or is it something which has more substance? Certainly the two-dimensional entropy argument shows you that there is more to it than that. And here is a helicity, which is a conserved quantity, which you have to show. That's the first exercise, and then use the triad to find the flux directions. And that should again, lead to something or other which is meaningful. So we'll see that if you do the homework, then we'll on Thursday see what this, what the inference is. So all right, the bottom line is that this is a very powerful tool, it seems. That if you understand, this Kolmogorov argument, that there is a question of flow from fluxes going, there is a conserved quantity. The conserved quantity can then be pumped. It can have, when it meets the forcing and dissipation, has this steady state feature which causes this flux from one end to the other, and the flux determines sets up in inertial region, determines the scaling property of various variables. So that's that's that. So now let's get into the same picture for the kind of flows that Mahendra Verma was talking about in the morning. So Mahendra's under stratified fluid under temperature gradient. So that's the last bit of this argument, the Kolmogorov bit that I want to do. Yeah, go ahead. The fact that there was the corresponding, the dissipative anomaly, which one talked about in the energy case. There is a similar, you would find that the entropy also has that kind of a dissipative anomaly, but the anomaly now leads to a different kind of singularity structure than in the energy. So apart from that, nothing else. The dissipative anomaly still exists. Right. So then, so from here then to fluid between two plates, z equal to 0 and z equal to d. And the temperature of this is held at T1. The temperature of this is held at T2. And the steady state profile is Ts is equal to T1 plus T2 minus T1 divided by T times delta, this is T1 minus T2 is what we'll call delta T. So this is T1 minus delta T d to Z. And this is delta T greater than 0, that is unstable situation, and that is heated from bottom. It's an unstable situation which gives rise to convection. So this is the convective case. And heated from above, so delta T is less than 0, heated from above, and it's a stable stratification. All right. So the equations of motion, del V del T plus V Boussinesq approximation, as was explained very clearly in the morning, Boussinesq, del that V equals V, better get signs right. Plus alpha G, let me put a mode of this times theta Z direction and plus V. So this is stable, and this is, there is rho naught, which is the sort of average tau density. And then there is del theta del T W is the Z component of velocity. So this is for the convective case of unstable layering. So it's dense top heavy and top heavy situation. And if it is, so the other stable stratification is the minus sign. So stable stratification is the minus sign. And right. So now what? So first, all that we have learned from the morning is that we need a conserved quantity. So conserved quantity, one has been tempted to look at energy. So you look at del T of integral V squared D3R plus a term over here integral, which has so many times we have shown that it is zero, that it is still zero, because Boussinesq tells you that divergence V is equal to zero. All the density variation has been taken care of in this term over here. The only role of density variation is to put that buoyancy drive, and thereafter it is divergence free, incompressible. So in this Boussinesq business, the large term is only the largest contribution of non-zero stratification, the density variation is taken care of completely in this term, and thereafter you merrily go and set divergence V equal to zero. That's the content of Boussinesq, which was very clearly brought out in the morning, so I have nothing further to add. Integral of this, we have million times shown today that this is zero. So nothing, once again, this is zero. And here comes this chap. And this is alpha G delta T. And it is theta and Z. That gives you V, only the Z component, which is integral. So I'm doing the convection case. So that is theta W V3R, and then this is your usual. Good. So all right. This doesn't have a in the inviscid limit, which is nu going to zero. There is a driving term over there, and therefore this is not a conserved quantity. Let's look at del T theta squared d3r. That's coming from this. With this condition over here, integral theta v dot grad theta is zero exactly for the reason that this is this integral is zero, and so I have integral w theta d3r minus lambda integral grad theta whole squared. But the point is that it doesn't, but this is a term which exists all over at every scale. I mean, it's as big as any term that you can be picking up. I mean, these quantities are all pretty big, arbitrarily big. So, I mean, this is not a negligible term in any way. I mean, we are talking about integrals over here, integral relations. And so integral relations, these are all largish terms, and an integral which is over all scales and nothing is small anywhere. I mean, it's a body force. But the external force, that's why we were very careful. I mean, that the external force that was being talked about was a stirring kind of force and not a body force. When, as soon as I have a body force, it is to be integrated over the entire volume. I mean, look, in this, nothing is small over here. I mean, over here, sure, I mean, I can make this nu go to zero, take the limit of very small, and then if this is to be finite, I have to have the grad. But now I have forcing over here, which unless theta and w are sort of out of phase and manage to cancel each other out through positives and negatives, I don't know whether it is small or not. Huh? Huh? There is no, there is no scale over here. I mean, this is an integral over the whole volume. It's a global thing now. I'm integrating it over the whole volume. Small, I mean, that can only be done after the end of the calculation, whether it is, I mean, a priori, I don't have any way of arguing that it is small. I mean, I don't even know its sign. It can be positive, it can be negative, and if there are positive, negative contributions at different parts of the cell, it can give me 0, but it will be accidental, not by any physical argument that I can give at this point. Yeah? No, but I'm not asking for, if I were to argue that I want a steady state for V square, then you would have to say that this is equal to this. But I have not asked for that right now. No? I have not asked that this be separately this and this. Right now, I can see that, look, I mean, your del del t V squared and d3r is this. And I mean, because I don't even know the sign of this term, na, I can't say that this is going to balance this. Maybe it will, maybe it will not. I have no argument. Huh? No, but that's... but that's an answer which you have done. Then you, but right now I'm arguing on the basis of just looking at it. And looking at it, I have no way of telling you whether it is positive or negative, or I mean, what sign it has. It's a integration over the entire cell. It's a good, I mean, issue that, I mean, do I have something positive definite over here and some, this is obviously negative definite? Can I have a... But it's non-zero, but this is, I mean, likely to be positive rather than, I mean, negative. But that, I mean, I guess what Pankaj is after, that if this is positive, this is certainly negative, then I can have kinetic energy balance by equating them. But a priori, I mean, I don't even know. But there is, I mean, I can immediately see on the other hand that del del t of V square minus it is alpha g delta t and theta square. This integral d3r is minus nu integral grad V square d3r plus lambda alpha g delta t integral grad theta square d3r. So this, I mean, this is certainly true, and in the inviscid limit, this is a dissipation, this is a dissipation. So no dissipation. I have the statement that V square minus alpha g delta t theta square, this is conserved. So that's certainly a conserved quantity. There is no doubt about that. That in the implicit limit, V square minus alpha g delta t theta square is a conserved quantity. Now, but But the point with this conserved quantity is that I don't even know the sign of this. This is where, I mean, the Kolmogorov argument which I had gone through with you and so far is absolutely useless over here because Kolmogorov says what we had been saying is find the whatever D3R which is conserved. So that was step one. So Kolmogorov says this is step one, and then step two should be no external forcing, del 2, this D3R, so is negative, and this whole thing is positive. It is only then, I mean, this has a definite sign, it's a positive quantity, and the right-hand side is negative, which means that this is going to decay with time, and the point would be that, all right, it is this negative part which has to do with dissipation, strong at small scales, and then I can add in a forcing which is good at large scales, and I can talk about a flux of this conserved quantity going from large scales, large length scales to small length scales. So growing over here, fed in over here, dissipated over here. But over here, this argument is completely lost. I don't know the sign of this quantity, which is the conserved quantity when when there is no dissipation. So once I don't know the sign, neither when I put in the dissipation over here, which is the right-hand side over here, so I don't know the sign whether this is positive definite, neither do I know whether this dissipation over here, what sign the so-called dissipation has. So I'm unable to tell you what the sign of the so-called conserved quantity is, or what the sign of this quantity is. Contrast this with the stable stratification. So the Kolmogorov argument as such is not at all useful in this case over here, unless, I mean, one can find a way of beating the system, but as such, I mean, the standard Kolmogorov argument goes nowhere. But then consider the stable stratification. If it's a stable stratification, I'll be through in 5 minutes. Take it. So if it's a stable stratification, then the sign is, it is the lower sign, and now, you see, for the stable stratification, it's a minus sign over here, and that means you are going to add. So what is going to happen for the stable stratification is that it is v squared by 2 plus alpha g delta t theta squared by 2 d3r is equal to minus integral nu grad v squared d3r minus lambda alpha g delta t. These are all mod signs, I mean, so no question any errors there. Grad theta squared d3r plus f, which is the forcing term which you have to put over here. The stable stratification, you need to have a forcing term over here to generate the turbulence. Otherwise, I mean, nothing's going to happen. So it is F dot V integral d3r. And now it's a very clear-cut situation. You have a quantity which this is a conserved quantity in the inviscid, the quantity which is v squared over 2 plus alpha g delta t mod theta squared by 2 is conserved if inviscid and unforced. So stable stratification is more like the usual case where it is this combination over here is a conserved quantity, and that's like now it is like a kinetic energy plus a potential energy, and you can have energy, kinetic energy getting transferred to this or back and forth. But this, as you can see over here, if you remember the Richardson number from the morning, that what you are seeing over here, barring some D's and so on, this is your Richardson number. And if this Richardson number is small, then it is the whole business over here is absolutely like the Kolmogorov argument that we had before. So Kolmogorov argument that one had for this problem is going to resurface when the Richardson number is small, and this is going to be essentially a kinetic energy flux dominated situation, more amount of things going into the kinetic energy rather than in the quote-unquote potential energy, and it is Kolmogorov. Then comes the situation where this becomes the sort of, these are on equal terms. Once these are on equal terms, you now have a situation where the this cannot be ignored anymore. The Richardson number builds up, starts playing an important role, and you have to rethink about that this is a conserved, this conserved quantity is, there is going to be a flux of this over here, and this flux of this quantity, what is it supposed to mean? So it's a question of what is the flux of this quantity going to be, and that is where this now becomes the technical issue, that this quantity is going to have a flux, and that flux, I mean, so this is the conserved quantity. In the inviscid limit, it is correctly dissipated. If I don't have any forcing over here, in the inviscid limit, it is correctly dissipated. So there is going to be a flux of this quantity from high wave from low wave numbers to high wave numbers, large scale, small to small scale, in length and in the distance length variable. And so this has all the features of this for a Kolmogorov argument to go through, but this is the chap which is flowing. The flux is of this quantity, and obviously for small Richardson number, it is the kinetic energy flux, and everything is dominated by V square. You see the Kolmogorov spectrum, you see. But what if these are competitive? That is when there is no, the answer is no longer straightforward. You have to check what is the flux of this quantity over here, which means you need to go back to the triads that we have been talking about and actually see what the triad for this whole mess is going to be. And the interesting which is what Mahendra mentioned in the morning, that this flux can be a scale independent. The flux of this can be scale independent in a very interesting way, that the whole thing is scale independent, not in the manner that each is individually scale independent, but this chap is scale independent, and this actually falls off as with increasing k. So it is the falling off of this and the constancy of this which gives rise to the picture of scale independent flux over here with what should be, I mean, asymptotic corrections coming from this non-negligible, from this sort of asymptotically negligible, but at finite largish case, not so small case, might have some, should have some effect coming out of this. So the flux of this is more conventional, but it is to be actually, you cannot argue that if this is scale, in the scale independence of this flux is an actual statement about the scale independence of both this and this, or whether it is the scale independence of this with a subdominant contribution coming from this. And what actually happens is that this is scale independent and this is subdominant when you see the Bolgiano business. If I go on increasing the Richardson number, bad, because now things become problematic. It is, I mean, it's you have heated, this is at a very high temperature, and this temperature over here being so, it would be almost impossible to start, I mean, the external forcing would have to be really weird to get the turbulence going over here. So that is a large Richardson numbers are somewhat have to be handled very differently. So small Richardson numbers, Kolmogorov variety, mid and Richardson numbers where these are more or less on equal status. That's the understandable equal, almost equal status of these two. That's more understandable, but requires little more work and shows some correction to the asymptotic behavior. But very high values of this, that's really, I mean, a completely dominant business coming from here, and not so clear really. The very high, which leads to a very high dissipation coefficient over here, and not very clear whether one would generate a small scale behavior, need to generate a small scale behavior out of this. So problematic, not at all. I mean, the various features of Kolmogorov, they are sort of present in some sense, but over here, but not as a complete whole picture which holds up. It does not at all work in the RBC over here, and the RBC has to be understood by looking at these individual fluxes and balances over there, rather than with rather than through a Kolmogorov kind of argument. Although the spectrum turns out Kolmogorov type, which is, I mean, offhand I don't know how to argue that, but I can see that it is not a conventional Kolmogorov kind of argument which can get you. Stable stratification is more along the Kolmogorov line that we have talked about, and it does show things which are interesting up to a point. The high Richardson number doesn't seem to be making, is once again not along the lines that one would have thought about. The anomalies are not there. This is not a workable proposition. So, but from small Richardson to intermediate Richardson, there is a Kolmogorov argument. but has to be bolstered by actual calculation of the fluxes. So that's the argument to here. Well, on Thursday, I'll look at this from a slightly different, the scale invariance of Navier-Stokes equation, which we have not talked about today, is another way of, because scaling laws are what we are after. So scale scale invariance of the solutions should be something which one should look for, and the possibilities that come out of that need to be explored. So that's going to give, that's going to supplement this discussion in some interesting fashion, and so we'll see. So that's the way things stand so far as a pure Kolmogorov argument goes. That's at least, that's the most, that's the best I know about how to handle Kolmogorov type of arguments for various cases that come up. And